Welcome back to Calculus 2. This section is an introduction to 3D coordinate systems. We want to understand 3D coordinates, and we're going to take a look at some specific shapes in 3 dimensions, points, planes, spheres, and we'll look at how to calculate distance in 3D. When we work with a 3D coordinate system, we use 3 axes. Instead of just having an x and y axis, we use 3, x, y, and z. And when we graph it out, it looks something like this. Instead of labeling this as x and y, we go in 3 dimensions and we add another axis, and it's hard to do this with a 2-dimensional piece of paper, but the other axis comes out of the page, something like this. And instead of labeling these x and y and then this new one z, we choose a slightly different labeling system. This is purely convention, but it's what everyone does, so we'll match the convention. The axis coming out of the page is going to be the x-axis. And then this is the y-axis here, and the one vertically is the z-axis. So if you imagine looking down vertically from the top of the z-axis, if you just imagine viewing the x and y axes vertically straight from above the z-axis, you would see the regular old 2D xy coordinate system. It might be a little bit counterintuitive, but this is how we choose to label the axes for 3D coordinate systems. We can keep track of this labeling using something called the right-hand rule. To understand the right-hand rule, take your right hand, make sure it's your right hand, not your left one, take your right hand and make a finger gun out of it. So it looks something like this. Here's the thumb, here's the index finger, and then take your other fingers and point them perpendicularly to your index finger, something like this. That's a terrible drawing of a hand. I'm an awful artist, but hopefully you kind of get the picture. The x-axis is your index finger. So the index finger is the x-axis. The y-axis is the other 3 fingers here. There's the y-axis. And then your thumb pointing vertically upward, that's the z-axis. So again, to make this, you kind of make a finger gun and then point your other 3 fingers perpendicularly to both your index finger and your thumb. We should really have perpendicular angles everywhere here. And if you do that, your index finger is the x-axis, the other 3 fingers are the y-axis, your thumb is the z-axis. The orientation's a little bit off here, but if you imagine taking this picture and kind of rotating it slightly, point the index finger in the direction of the x-axis, the other 3 fingers in the direction of the y-axis, and then the thumb vertically in the direction of the z-axis, and there you have the proper labeling for the 3D coordinate system. This really is a pathetic drawing of a hand, isn't it? Let me see if I can do a little bit better. Hang on just a second. There we go. That's a much better drawing, which was most definitely hand-drawn by me. Of course, certainly didn't just Google search right-hand rule and copy the first picture I saw. Anyway, so there we have it. There's the right-hand rule. This might look a little bit confusing because just the way that the orientation is, it looks like the index finger is actually pointing in the direction of the y-axis. It looks like the middle finger is pointing in the direction of the x-axis. And, well, the thumb's fine, but it looks like x and y have been switched around. But the fingers have to point in the same positive direction. So positive x direction is this way, positive y direction is this way. So in order to get this picture to match the picture that we just drew, you'd have to sort of rotate the hand a little bit this way, about 90 degrees, and then the index finger would be pointing in the same direction as the x-axis. All the other axes would work out. Let's talk about some more terminology for 3-dimensional coordinate systems. Instead of quadrants, which is what we have with 2 dimensions, we have octants. So there are 4 quadrants with 2 dimensions. In 3 dimensions, there are 8 octants. And we could think about labeling them, but we're not really too concerned about what the labels of the different octants are. But we can think of 8 different places in the 3-dimensional space. It's hard to visualize it here in 2 dimensions, but there'd be 1, 2, 3, 4, and then 1, 2, 3, 4 down below the x and y axes here. So 8 different octants. Really, it's quite difficult to visualize 3-dimensional representations just on a 2-dimensional plane like this. So something that's really, really helpful when we're working with 3-dimensional objects is to use some sort of graphing software. And if you go to geogebra.org/3D, this is a free online 3-dimensional graphing platform. GeoGebra is sort of like Desmos. It's not quite as intuitive, but at this time, unfortunately, Desmos does not have 3-dimensional graphing capabilities. Hopefully it will in the future. But geogebra.org/3D, it's not too difficult to work with, and I'll show you some examples in a little bit. So being able to visualize 3-dimensional shapes using graphing software is really, really helpful. Let's talk about some more terms. In 2 dimensions, the 2D Cartesian coordinate system, the xy plane, is called R2. R stands for real numbers. So R2, that's a symbol that we use to talk about the xy plane. This consists of all ordered pairs, x and y, where xy are real numbers. This is just the regular old xy plane that we're used to working with. 3-dimensional space is called R3. And instead of consisting of pairs, 3-dimensional space consists of all ordered triples. X, y, z. All the different places in the 3-dimensional space can be described with a 3-dimensional point, a triple. X, y, and z can be any real numbers, and this describes all of the 3-dimensional space. In 2 dimensions, when we try to graph an equation with x's and y's, the shape that we get is a curve. In 3 dimensions, when we have an equation that relates x, y, and z, the shape that's produced is a surface. It's a 3-dimensional surface rather than just a curve. In just a bit, we're going to talk about some important 3-dimensional objects, points, planes, and spheres. But before we do that, I want to show you some visualizations in GeoGebra to help us understand 3D coordinate systems a little bit better visually. This is the GeoGebra 3D Calculator app for iPad. It doesn't work quite as well as the website. It has some glitches, but it works well enough, so I want to show you some things here. So we have the 3 different axes there. The x-axis is red, y-axis green, and z-axis blue. If you take your right hand and point your index finger in the direction of the red axis, and your thumb points in the direction of the z-axis, and the rest of your fingers point in the direction of the y-axis. So we're drawing this according to the right-hand rule. We just want to take a look at some different graphs here, and we'll explore some of the different forms a little more in depth. We just want to visualize some cool things here in GeoGebra. So first of all, let's look at a plane. This is this equation 3 here, 2x minus 4y plus z equals 2. There's a plane. It extends infinitely in all directions. Let's look at another plane, y equals 3. This is missing some variables. This is missing the x and z. So if y equals 3, x and z can be whatever they want. So you see in the blue and red directions, we can have any point vertically and horizontally as long as y equals 3. So these are all the y values or all the x and z values where y equals 3. That's that plane y equals 3. Let's take a look at a point. To plot a point in GeoGebra, you just do an ordered triple. So this is 1, negative 3, 6. And if we look in the x direction, the red axis, we see 1 in the x direction, negative 3 in the y direction, that's the green axis. And then we're going up vertically 6 in the z direction, that's that blue axis there. So there's a point. Let's take a look at a circle, equation 2 here. This is x minus 2 quantity squared plus y plus 1 quantity squared plus z minus 3 quantity squared, I believe equals 4. So this gives us a circle. The center is at x equals positive 2. That's positive 2 in the red axis direction. Y equals negative 1. And then in the positive z direction, z equals 3. Radius of 2. Let's take a look at some more exotic graphs here. How about z equals x squared? What does that look like? Oh, it's this parabolic shape. We're missing a y here. If we have z equals x squared, y can be anything. So we get this parabola that's just extruded along the y-axis in all directions. So z equals x squared, and y can be anything it wants to be. Let's take a look at some more interesting ones. How about z equals x squared plus y squared? We get that shape. That's called a paraboloid. If z equals x squared minus y squared, we get that shape. It's a saddle shape, or it's also called a hyperbolic paraboloid, which is just a really cool name. And take a look at this. If we graph x squared minus y squared along with x squared plus y squared, that nose cone, that paraboloid, just fits right snugly into the hyperbolic paraboloid. How about x equals z squared minus 4y? It's like a slanted sideways extruded parabola. Okay, a couple really, really cool looking ones. Z equals sine of x plus cosine of y. We get this wavy, bumpy, it almost looks like an egg carton. You know, if you put the eggs in the different places, it almost looks like something that you could put eggs in, or like a special packing foam, I don't know. But z equals sine of x plus cosine of y, we get that graph. And then z equals sine of xy. Whoa, we get this. That's super cool. So for these more exotic graphs here, don't worry about these now. You'll see some of these sorts of things if you go on to take multidimensional calculus, and you'll understand how to work with some of these different surfaces. But we just want to be able to visualize them a little bit and appreciate how very nifty they are. Now that we've seen some three-dimensional shapes in GeoGebra, let's take a look a little bit more specifically at points, planes, and spheres. A point in 3 dimensions. Well, it's sort of like a point in 2 dimensions, except we add a z variable. So it's just an ordered triple. And if we were to graph what this looks like in 3 dimensions, let's just graph our axes here. This is good practice for labeling. Here's the x-axis, here's the y-axis, here's the z-axis. So a point, ABC, let's just put a generic point out here. Kind of tricky to visualize, but let's just think of the point ABC. We go a distance of a in the x direction, so a in the x direction, then a distance of b in the y direction, and then a distance of z vertically in the z direction. So this would be an x distance of a, y distance of b, a z distance of c. That gives us this point ABC. It's tricky to visualize on a two-dimensional piece of paper or screen, so play around in GeoGebra graphing some different points and being comfortable with what three-dimensional points look like. A plane has this form. X, Y, and Z are variables here, and the A, B, C, D, those are just numbers, whatever constants we want. So if we have something times X plus something times Y plus something times Z equal to some other number, that gives us a plane extending infinitely in all directions. That's a plane. A sphere, if we want to choose a specific center, let's just choose ABC as the center, we can create a sphere really analogously to a circle in 2 dimensions. Imagine taking a circle. Let's think of centering it at the point AB. So let's just say this is A, so an x distance of A, and then a y distance of B. So we have a circle centered at AB. Let's just say it has a radius of r. The equation for this circle would be x minus a, quantity squared, plus y minus b squared equals r squared. And we can see the similarity between this equation for a circle in 2 dimensions and the equation for a sphere in 3 dimensions. We're just adding another term here, z minus c squared. So here's the general form of a sphere in 3 dimensions, centered at ABC with a radius of r. How do we find the distance between 2 points in 3 dimensions? Let's say we have a point x1, y1, z1 and another point x2, y2, z2. Here's the formula for distance, and I hope this looks somewhat familiar. If you ignore this part of the formula, then what you're left with is the distance formula in 2 dimensions. So to generalize to 3 dimensions, we just add this third component here, this third term, take the square root of everything, and we have the distance formula in 3 dimensions. This formula actually comes from the Pythagorean theorem. I'd like to take a minute to explain why this formula is true. So let's draw our x, y, z axes. We'll draw a couple points. It's going to be a little tricky to visualize, but I think we can manage. So here's the x and the y and the z axes. Let's just think of a point here. This is the point x1, y1, z1. And we'll think of another point, maybe up here, which is x2, y2, z2. I want to find the distance between these 2 points. So we're going to think of a horizontal or an x distance rather, something like this, parallel to the x-axis. And then we move a y distance until we're right underneath the point. And then we move up vertically a z distance. We can label what these different distances are. If we go along the x-axis, we're not changing y or z, we're just changing x here. So we're moving from x1 to x2. This length is x2 minus x1. Really, we'd probably need to use absolute values, but if x2 is larger, we can just call this length x2 minus x1. When we move in the y direction from here over to this point here, we're not changing the x or z values. So the difference, or the length here, would just be the difference between the y values. That length is y2 minus y1. Again, we should probably use absolute values in general, but we're going to be squaring these, so it ultimately doesn't really matter. The difference in height here is just the difference in the z variables. That would be z2 minus z1. First thing I'm going to do is to find the distance between this point here and this point here. There's no change in z here, it's just a change in x and y. This would literally be the distance formula for 2 dimensions, which we should know. The way to get this is the Pythagorean theorem. We can imagine here having a triangle. We've got a right angle right here, and the hypotenuse of the triangle is this distance that we just drew in here. How do we find the distance of the hypotenuse? We take one leg squared plus the other leg squared, take the square root. That will give us this distance d. Let's just call that lowercase d for now. So small d is the square root of x2 minus x1 squared plus y2 minus y1 squared. That's this distance. It lies in the xy plane, so it's perfectly flat here. It's not moving vertically at all. Now think of this distance here. That's actually the distance that we want between these 2 points. That's what we're ultimately looking to find, the distance in 3 dimensions. How can we find that? Well, we have another right triangle here. Tricky to visualize, but think of this right triangle. We have a right angle right here. And again, we can use the Pythagorean theorem. We take this distance squared plus this distance squared, take the square root of that. That will give us the distance that we want. So let's call this one capital D. This is the distance in 3 dimensions. And that distance will be the square root of, so our triangle once again, we have leg, leg, right angle between them, and then hypotenuse. So we're using the Pythagorean theorem. D squared plus z2 minus z1 squared equals capital D squared, the length that we want. So we take the square root of d squared. Well, here's d, so if we square d, we just get rid of the square root symbol. So d squared is simply x2 minus x1 squared plus y2 minus y1 squared. So that would be one leg of the triangle. We add the second leg squared of the triangle, so we add z2 minus z1 squared. Take the square root of everything. From the Pythagorean theorem, we have the distance in 3 dimensions. Look at this. This is the formula right here. It's the distance between 2 points in 3 dimensions. In the next video, we're going to look at using these concepts for some specific examples.
It looks something like this. I'm going to do my best attempt at a drawing of a hand, which is really bad because I'm a terrible artist. So there's a thumb. Whoops. So it looks something like this. And then take your other 3 fingers. So you've got your index finger. That's going to be the x-axis. The thumb will be the y-axis. And then the other fingers, kind of point them perpendicular to your index finger. Something like this. That's a terrible drawing of a hand, but hopefully you get the picture. So we have the x-axis as the thumb. The x-axis as... So we have the x-axis as the index finger. Why did you label this wrong? That's not the right labeling. You're so stupid.